bed or some other arbitrary depth. So this is how this tau.u connects to the kinetic energy, the turbulent kinetic energy equation and the mean kinetic energy equation. We have this other component, this wave supported component. And that's really, you can think of that as coming from the del.t term in this top equation here. This is the transport divergence. And the transport divergence has two main components. This first term, E prime W prime, this is the turbulent kinetic energy flux. So E prime here is the TKE, W prime is the fluctuating vertical component. And then there's the second term, the pressure work, which is P prime W prime, which I'm going to focus on here. This integral is a little bit easier to see. You just get the argument at the bounds of the integral. And I'm going to focus here on the P prime W prime right at the wavy surface. You can think of the W at the interface as the same thing as the d eta dt, the vertical fluctuating component from wave elevations. And you can also relate that to the wave slope times the wave phase speed. So when you do that and you put it back into this term, we have a P prime d eta dx, which is pressure times the surface slope. And you might be familiar with this, which is basically the definition of the form drag or the pressure supported drag tau. And then it's multiplied by the wave phase speed c. So, the reason that the wave supported component is so much bigger than the tau.u component is just because phase speeds of waves tend to be much larger than the mean surface currents u. So, So what happens to this wave supported energy at the surface? Well, for the most part, it actually takes a lot of space or a large fetch to grow surface waves. And most of the energy supported by surface waves is dissipated locally. This is called wind wave equilibrium. And in the wave community, we think of this as a spectral balance between the frequency dependent wind input, dissipation, and nonlinear transfer terms. When you integrate over the energy spectrum, the nonlinear transfer terms mostly go to zero, and so that you have flux into the ocean surface that's nearly equivalent to this amount that's supported on the atmospheric side. This is primarily kept to a thin layer really close to the surface, and many studies in the past have shown that this is mostly transferred to turbulent kinetic energy dissipation rates, epsilon, in the upper couple meters, something on the order of a wave height. So there's growing evidence that the balance in this wave affected layer, the wave dissipation layer, is also between the transport divergence components, this del.t, and the TKE dissipation rate. Most studies measure epsilon directly and show that it can't be explained by something like the shear production, the shear scaling, or the buoyancy production or buoyancy scaling alone. I kind of want to highlight, I think this study is really interesting. The Scully et al. Study is the only one that I'm aware of that directly measured the transport divergence terms and found that they actually do balance epsilon in the upper layer here. So if you haven't seen this, I think it's quite interesting. Suggest you take a look. So what about the rest? That wave affected layer accounts for the majority of this flux that's supported by the surface gravity waves, but we still have this other flux that's supported by mostly the surface currents. And this is what the focus of the rest of my talk is going to be mainly about. So I'd like to look at this with mooring data from the Spurs 1 mooring. Excuse me. This is a really awesome data set. It has a full MET package for fluxes at the surface, so surface stress, surface buoyancy flux. The buoy has measurements of the wave spectrum and a really densely instrumented mooring chain in the upper ocean, including CT measurements, so you can determine mixed layer depths. It has ADCPs and currents meters, so you can get profiles of current velocity, and some novel measurements of dissipation rate that I'm going to talk about next. So with the measured profiles of U and Z in the wave spectrum, combined with the surface stress, we can get estimates of P and P Stokes here if we assume a vertical shape of the decay of the stress. So this is just kind of an approximation. We recognize that there's limitations to the linear decaying stress throughout the layer, but simply when we're applying this to estimate the integrated Stokes production, that it gets us fairly close, that the effects of the curvature of tower tend to be smaller than the the direct measured profiles of currents. I'm also going to, I mentioned this wave affected layer, but where we have the importance of the transport terms of the dissipation rate, those are mostly contained to a thin layer on the order of a few wave heights. But below that layer, we're going to assume that the transport divergence terms are actually small. And I'm going to call this depth at which this transition occurs, Z sub t. We're basically above this depth. The primary balance is between transport divergence and epsilon. And below that depth, the transport divergence terms are small relative to the other terms. So that leaves this epsilon term, the vertical integral of epsilon, which can be challenging to estimate. And I'm going to overview some new methods that were published on just last year in 2021. This was a kind of a long ongoing effort started by Tom and Chris Zappa to integrate pulse coherent ADCPs along the mooring chain. This is a sort of schematic in the top left here. There's a vertical titanium bar that connects to the rest of the mooring. The ADCP has a fin, and it can swivel on these Delrin connections so that it can point, the beam can point upflow and avoid its own wake. And the idea here is to fit direct number spectra to the inertial subrange. So on the top right here, you can see a model spectrum. This is the Pope spectrum, which has these shape functions for the low wave numbers and the high wave numbers in the dissipation range. In the inertial subrange, these are close to 1, and this tends to be on the scale of sort of the meter to 2 meter scales that we're looking at with the aquadops. There's a lot of processing steps that I don't want to spend all of my time going over, that include velocity unwrapping from the pulse coherent method. There needs to be a lot of quality control of the velocity measurements, and then there's an instrument response function that you have to account for when you do wave number spectrum fits. All of that is referred to in this JTech paper, and I'm going to just skip a lot of that and show you some of the results which we compared with Lou St. Laurent's microstructure glider, which was around near the Spurs 1 mooring for 2 different 2-week deployments. So here, the 2 time series are different depths where the aquadops were on the mooring chain, and the equivalent depths from the glider during its 2-week deployments. The glider dissipation rates are in blue, the mooring dissipation rates are in orange, and the estimate for the surface buoyancy, convective buoyancy flux, are these gray squares. So, as you can see, the mooring is certainly noisier than the glider, but it's fairly good above this gray shaded region, which is where we kind of expect the noise floor for the mooring to be approximately. And I have these different box sections where we actually see a lot more disagreement. But if you look at the 2 measured temperature profiles, a lot of these periods coincide with where there's different vertical temperature structures. So for example, here in this red box, you can see in the top P color, the glider has some near surface temperature structure indicating stratification. The mooring doesn't really see this near surface stratification. And during those conditions, the glider below that stratification has much lower turbulence levels, whereas the mooring has kind of no stratification above that depth and matches the surface buoyancy flux during this nighttime convection condition. You can do a direct comparison of the two estimates. So here the mooring measured dissipation rates are on the vertical axis, the glider microstructure shear estimated dissipation rates are on the horizontal axis. Dashed black line is 1-to-1. The dashed gray lines are like the roughly a factor of 2 difference. That's kind of the amount of standard error that folks tend to see when they compare dissipation rates to each other. And so we're doing pretty good above this 10⁻⁸ value, which is about where we expect the noise floor of the aqueducts to be. So, dissipation rates are definitely noisy. These are bin averages. The vertical bars are twice the standard error. But if you compare, there's past studies that have compared dissipation rates to each other, and they look kind of similarly. This is a paper from Moom et al. In '95. They compared a APL microstructure to a nearby OSU microstructure, and they kind of agreed on average, but there's a lot of scatter, and there's this kind of systematic bias that's somewhere within a factor of 2. So we think our dissipation rates here are good to about a factor of 2 when you're above 10⁻⁸. So that I showed the first deployment. There's a second glider deployment. I'm going to skip over this quickly so that we can get to some of the other results in the allotted time, but you see a pretty similar result here. The scatter plot about 10⁻⁸ is where you stop seeing this correlation between the two dissipation rate estimates. Above 10⁻⁸, they seem fairly well correlated within this kind of factor of 2. That's fairly common when you compare two sets of turbulence estimates. And the result from this work is that we can make things like this contour plot of TKE dissipation rates for nearly an entire year. I actually realized, I apologize, the time label got removed here. This Spurs 1 mooring, the start of this is in the end of September in 2012, and the end of this dissipation record, I believe, is around October. In July, the surface 10-meter aqueduct stopped reporting, and that's this this little step right here is the beginning of July. The green line here, this is an estimate of the wave affected layer that's based on the surface wave significant wave height, and the gray line is the mixed layer depth that's determined from the temperature difference. So you can see that the dissipation rates are generally larger above the mixed layer depth, tend to be below 10⁻⁸, which is about our noise floor when you're below the mixed layer depth. But from this, we can estimate this integrated epsilon term and go back and apply that towards this vertically integrated TKE budget. So this is a compiled figure. I've added these top 2 panels. This is the 24-hour mean surface fluxes from the mooring. So the top panel is tau, the wind stress. The panel B here is the buoyancy flux. The middle panel, panel C, is the magnitude of the currents. This is derived from multiple ADCPs and currents meters that are along the mooring chain. Panel D here, this is the plot I just showed on the previous slide, contours of the dissipation rates. And then this bottom panel I'd like to draw your attention to. This is where we can estimate the vertical integration of epsilon from the mixed layer depth to this wave affected layer depth, which is the green line in panel D. Compare that to our estimates of the shear production, Stokes production, and buoyancy flux using this kind of simplified linear decay model from the surface. So you can see for the most part, the dissipation rates are somewhat noisy, but for the most part, they seem to agree fairly well throughout most of this year, from roughly September through August. Sorry, in July, you can see when the surface 10-meter dissipation rate, the aqueduct stopped reporting. We start, you have to extrapolate, and the extrapolation just really doesn't work super well. And so we cut off the rest of the analysis here in July when we don't have this near surface estimate of dissipation rate. Again, you can just see the relationship a little more clearly if you plot the two terms directly against each other. So the vertical axis here is the TKE dissipation rate integrated from the mixed layer depth to this transition layer, CT. The horizontal axis here is the sum of these different terms, the production, Stokes production, and buoyancy flux with the assumed linear decay models. And the open circles here are the daily averages from this analysis. You can do bin averages in the dark black circles, and they're all fairly close to this 1-to-1 line, which is the dashed black line. So I know this transition depth that I've defined is somewhat arbitrary. I didn't go through it too much. And to be honest, it doesn't matter. Well, it's pretty robust for choosing different transition depths as long as they are lower than when you expect the balance of transport divergence and epsilon to take over near the surface. So you can set it smaller, farther away from the surface, use something large like 10 significant wave heights, which is shown with these blue solid circles, and you still get good agreement from these integrated budgets. All right, so this is all, this was published recently in the GRL paper. I'm going to show some slides. One figure next that didn't quite make it in, but I was interested in tying this back to what I mentioned, these sort of global surface fluxes. And I was curious how much of this dissipation rate is from essentially from the tau.u term. So if you remember, you can break apart the integrated surface production into these tau.u components, and from the u.d tau dz component from this linear decaying stress model. The stress at the base of the layer becomes 0, and you can plot the estimates of the surface KE flux, the tau.u estimated with the mooring data, against the amount that we're estimating goes into total production here, which is basically the tau.u minus the mean production term u.d tau dz. So there seems to be pretty good agreement when tau.u is positive that it's roughly a half of the surface KE flux seems to appear as turbulence production. Kind of interesting to note that tau.u is not always positive at the surface, that you have times where there's light winds, strong ocean currents exist that are driven from non-wind processes or wind processes occurring in different locations. And in this case, the turbulence doesn't go negative, which would be a little nonsensical. It just is supported not from the surface down, but from below going up. And so the negative tau.u at the surface is supported by an upward flux from the mean, from the general ocean circulation. A lot of studies parameterize the surface flux as a U star cubed. And so I was kind of interested in how these two relate. They're very well correlated, this integrated estimate of the production and the U star cubed, with a couple exceptions. At really low values of energy fluxes, you'll see that these are kind of associated with the negative tau.u. You kind of lose this correlation between U star cubed and the integrated turbulence production, which makes sense. The flux is coming from the general ocean circulation going upwards and not from the wind downwards. And then kind of interesting, at the highest value of energy levels, you kind of have this deviation where it seems like there's more production than can be supported from U star cubed. I forgot to mention here, the dashed black line is the 1-to-1. The dashed red line is U star cubed over 0.4, which folks probably recognize as von Karman's constant. So this is in support of kind of the U star cubed over kappa scaling that most folks are familiar with. So I think I see a ping in the chat, but I'm just about done, so I'll summarize and then we can get to this. So as just a quick summary, estimated terms in the vertically integrated TKE equation from 10 months of mooring data, including these novel estimates of TKE dissipation rate, and that these measured dissipation rates balance the surface-driven forcing with a simple linear decaying shape function to roughly within a factor of 2. And this is kind of as good as we think these dissipation rates are getting right now. This is somewhat consistent with when folks compare epsilon to other estimates of epsilon, they kind of come up with this factor of 2 in the mean error there. So, and then this last slide, it seems like roughly half of that surface KE flux, that tau.u, is entered as production for turbulence in that mixed layer below the wave affected layer. So thank you, and happy to take questions.
Thank you. This is great. So yeah, a round of applause, as it were. And are there questions for Seth?
I realize it's early on the West Coast, so appreciate folks getting up early to tune in and understand if you're sleepy and haven't formed questions yet as well.
I have a question, Sarah.
Yeah, go ahead.
So, Seth, I'm going to ask you a big picture question. And in fact, it's a question for everyone to think about. What if we could measure surface currents at the very surface? And, you know, we want to relate it to large scale ocean processes that like span the mixed layer depth. You know, what do you think about sort of getting from Z equals 0 to kind of bulk mixed layer processes? What are the, what's your take on that?
Yeah, great question, Tom. You know, I think the ability to do that depends on some of the things for this analysis that were directly measured, like the vertical structure of currents that are really dependent on turbulent processes, some of which I'm not sure how well we have characterized that, but you can do things like the slab model from Ewer and Al's 2006 paper, I believe, you know, that kind of, yeah, I guess I'm not sure how big the error is in some of these assumptions you would have to make on kind of the vertical structure of things, but I'm sure maybe that's something that could be quantified with more work or with support modeling or something like that.
If I can ask sort of a follow-up to that, you show this amazing relationship where you're finding that half of tau.u is linked to the kinetic energy flux, or it's half the kinetic energy. Why half? Any ideas? Should that be robust?
Yeah, I don't know. And I think you know, that's not something that was published. And I think in part there's probably more things to check on that. You know, that would actually be a relatively efficient process, I think. You know, I think inefficient processes, you would think most of it is just making turbulence. You know, I think sometimes folks assume things like wave breaking at the surface or micro breakers that have this really massive energy flux are less efficient and seem to just make a lot of turbulence that doesn't sort of energize mean currents quite as much. And so it's, yeah, it's interesting. It is kind of consistent with, other boundary layer theory. I think what really struck me is that you get something that's basically von Karman's constant with the U star cubed relation. And so it's it seems like yeah, maybe there's something about shear driven turbulence that kind of gives you this roughly equal partition of energy. I'm not sure. But like I said, that's one component that I felt like be happy to talk with folks here about it, but probably deserves more thought about the efficiency of those that energy transfer.
Melanie, you have a question?
Yeah, hi. Interesting talk, Seth, and really interesting measurements, all of you who were involved. Let me remember to take down my hand like I never do. So just thinking about this partitioning, I also thought that the factor of 1/2 was a really interesting result. And thinking about, maybe can you say a little more, I'm not quite awake, about that and whether, and if so, how it's related to the divergence term that Malcolm Scully calculated that you mentioned. I'm thinking that is a separate thing, but is that related to what Shui Chen has talked about, that only about 80% of the energy put into the surface by the wind stress goes into the processes you're talking about, and she was saying about 20% of it propagates away as waves, and so we shouldn't expect a local stress balance across the interface, but she's talking about models, right? So are any 2 or 3 of those 3 things related, and do you have comments?
Yeah, I was trying to take a really observationally focused approach to this, and the transport terms are really tricky. They're very hard to measure directly, and I feel like they are how do I put this? I guess I think there's still sort of a mystery in some of, especially the way we tend to model turbulence. I think if you do like a RANS model, usually this is where you apply some closure scheme. And the interesting part of Malcolm Scully's paper was it was really, I think a lot of the wave breaking models and things like Craig and Banner 94 assume that there's the transport term is a TKE gradient flux. So you have a gradient in TKE because you have a strong flux at the surface and less TKE lower down, and that there's some, eddy diffusion that for the TKA flux. But Malcolm Scully's paper was saying that it's actually not that kind of implies that it's this E prime W prime term, that it's like the self advection of turbulence essentially. But Malcolm found that it was mostly driven by the pressure term, that it was the P prime W prime on the water side that was somehow larger than this. It's actually very related to the E prime W prime term, and I think there's a lot of reasons where under normal conditions they should be equal and opposite, and the transport term should be small, but there's something about likely related to the wave field that kind of breaks that asymmetry, and it's a little bit of an unknown black box to me at the surface, to be honest. So it's actually the focus of some ongoing work I have. We're doing a project deployment this spring to try and estimate that again with Malcolm, and so maybe we can tell you more next year. But the other thing I think I wanted to mention is that I feel like if you look at more of a like an equation for Reynolds stress, which is not really included in the TKE equation, we're kind of looking at the trace of the Reynolds stress tensor. so the effects of Langer there are in how it sets the anisotropy. So you get different, vertical variance compared to the U star under strong Langer conditions that a lot of Eric Desaro's work has shown. And that isn't really reflected in the TKE equation. And so it could be that this is buried in some of these transport terms, and why you get the kind of vertical structure of currents that we measured here, but you might have to assume if you were, measuring the surface current and trying to propagate information downwards from a satellite mission. So I think there's a lot of knowledge that could be learned in kind of that sphere. And those are the things that are really, really hard to measure, especially from things like a mooring, right? Where, Tom and I have talked about this for a long time about how to get these dissipation rates to be somewhat reasonable, and, going after things like the Reynolds stress or the anisotropy. And it's just really measurement. It's a really difficult measurement problem. So, yeah.
Thanks.
I see there's another hand up. Ken Hughes.
Hey, Seth. So I know you kind of touched on it, but I couldn't quite follow. Why was it that when that near surface stratification came up, the mooring dissipations didn't go down like the glider ones did?
So, yeah, I think so when there were a few periods, which was a little bit strange, where it was nighttime, and you might expect nighttime convection to kind of deepen that stratification. And the glider temperature measurements still showed some near surface stratification, even though it was nighttime. And below the stratification, the dissipation rates were quite small, something like minus 10 or something like that, minus 9, something like that. So I think it was almost weirder to see the stratification during some of the nighttime records, and the mooring, had much higher dissipation rates, but they're consistent with the kind of convective buoyancy flux at the surface at night, and it didn't really measure this stratification in the upper temperature sensors. So, I think when Tom and I talked about this, we were more confused about why there was temperature structure in the glider data more so than it seemed consistent to us that the turbulence matched sort of nighttime convection conditions. And, I didn't really diagnose that too much. I think Alec Bogdanov's thesis talks about that data a lot more and has some theories about why that might be happening and might be the case, but it's kind of perplexing, isn't it?
Right.
Seth, could you show the figure
Yes.
so that we can see what Ken is talking about?
Yes, here we go. So this is, are folks seeing the correct screen here?
No, we need the display swapped.
All right, second here. Let's try this again. How about now?
Yep.
So this is, I think, what I was talking about. This is the glider measured temperature. And on the September 30th, you can see the daytime, the stratification sets up, and then it kind of decreases over the nighttime, but there's still this kind of remnant surface layer. The mooring doesn't really see this temperature stratification on the surface. And then at the dissipation rates, it's noisy, but the mooring is kind of scattered around this surface buoyancy flux from the JB. I apologize, I'm not consistent with my notation here. This is B naught from the notation I gave earlier. There's kind of scatter around this expected value from convection, but the glider is kind of between 10 to the minus 9, 10 to the minus 10 below there. What in that layer seems to be stratification near the surface. So I think the stratification is the theory would be if there's stratification, it kind of blocks the turbulence that's driven from the surface from propagating lower in the water column. And when you don't see that stratification, then you might expect the turbulence to be able to propagate downward and set higher levels of turbulence. And I think the
Cool.
weird
Yeah,
thing is that, go ahead.
I was just going to say that makes a lot more sense. I didn't quite notice that there was clear differences in the stratification between the two measurements.
Yeah. So yeah, and Tom made this really nice figure for that paper where he showed some satellite temperature data from kind of around nearby that period, and there was definitely some horizontal structure in the temperature signal from satellite data. So we think that, even though they're a couple kilometers apart, there's just horizontal structure that means that there's different kind of vertical profiles of both turbulence and temperature.
Actually, Seth, I was just going to ask about the horizontal structure. Did you, even though there, the separation isn't that large, did you actually look at how different the dissipation rates are as a function of spatial separation?
A little bit. I think, the issue is that the mooring derived dissipation rates just have a lot more variance. They're a lot noisier, and when you have a year-long record, you can average a lot and get these kind of mean plots that I've shown for the energy budget for 2 weeks of data with, half of it at a couple kilometers and half of it a little closer. It was, if you squinted, maybe it got worse when they were farther away, but I'm not sure I would publish it. I guess I'll say that. So,
right. Can I ask one other question?
Yeah, go ahead.
The other long time series of dissipation, especially from gliders, that I know came out recently was the Gwyn Evans paper from the osmosis site. Are they big? Did you see any differences between the two? I've not had a chance to compare your paper to his yet.
I actually haven't seen that paper, but I'll definitely take a look. So
Okay.
is that a 2021 paper?
Let me see if I can find the link. I'll pop it in the chat for you.
That would be awesome. Thank you.
If I can ask one more question, I'm thinking back to this question, what could it be measured from space? You've shown this nice relationship or tau.u type term that seems to have some useful quantity. How accurate do you need tau and u to get the sorts of results you're showing?
Yeah, that's a good question. So I used the bulk fluxes from the mooring, and I think the bulk fluxes, when you're doing this type of analysis, might actually be a little bit cleaner. But the surface current is actually a little harder to do. Like a true surface current, it's pretty hard to do from a mooring. It's moving around. You have to put something, trying to avoid wake issues and things like that. So in some ways, it might be better to do it. It might be more clear if you get it, closer to a true surface current, and avoids any issues if there's stratification in the upper couple of meters. Excuse me. There's some paper by there's not too much that's been published, I think, and really, really near surface stratification on the scales of what you'd get from a remotely sensed product compared to collections of drifters or near surface ADCP measurements. But there's one by Nathan, I always mispronounce his last name, so I apologize, Laxigue, I think. He was a student or a postdoc with Zappa at Lamont, and now he's at UNH, and he had a nice analysis where he compared drifters that had different vertical extents and some remotely sensed surface current products and ADCP measurements. And that paper seemed to suggest that there could be a decent amount of shear and even the upper, couple centimeters. So I think in some ways you would be more accurate depending on the levels of shear, which are somewhat unknown generally. I think it could be more accurate to get at that energy flux tau.u term if you had better surface currents. Obviously there's, some sort of area integration. You have a footprint for the satellite. It's going to be much bigger than sort of the mooring footprint. But You know, if it's kind of the competing effects of the, you know, horizontal variability that you're averaging over, and, you know, the amount of vertical shear that's kind of unknown from some of these mooring products. So it's an interesting question. I think it's yeah. Have to think about, there's a lot of things to think about, I guess, comparing the two. So
Yeah, one to keep us up at night, I guess.
Great.
Are there other
The link for
questions?
this paper.
If not, I'll thank everybody for participating. We had originally thought we'd have another webinar in this series next week, but we've put that off. And so the next one will be in 2 weeks, and it'll be Tom Farrar talking about lessons from S mode. So we'll hope to see you all then. Thank you
Thank you,
very much,
everybody,
Seth.
and
Really
appreciate you getting
it.
up early for me on the West Coast there.
Yeah, great talk. Really enjoyable, interesting stuff.
Thank you so much. Take care, everybody.
Thanks a lot, Seth. And thanks everyone for organizing too. Good to see you all.
Hi, everyone.